Einstein realized that not only does time slow down the faster you go, he also realized that when objects move, they get heavier as they move. It was a curiosity. Why should objects get heavier as they move? And then he suddenly realized that the reason why objects get heavier as they move is because the energy of motion is being converted into mass. Now think about that for a moment. The energy of motion is being converted into mass. This means that energy is turning into mass, and mass is turning into energy. And Einstein quickly wrote down, it's only one step, quickly wrote down the equation that relates energy to matter, and it is exactly E equals mc squared. According to the quantum theory, even the most bizarre events have a probability of taking place. There's a certain probability that I will dissolve and simply rematerialize on the other side of that brick wall. Now, you may say to yourself, well, that's impossible. We've never seen anyone dissolve and rematerialize on the other side of brick walls. But we actually give this problem to our graduate students. To our PhD candidates, we ask them to calculate, using the quantum theory, what is the probability that you will find yourself on the other side of a brick wall? Now, to tell you the truth, you would have to wait longer than the lifetime of the universe for such an event to take place. So you don't have to worry. Your atoms are not going to dissolve, and you're not going to rematerialize on the other side of brick walls. But there is a probability you can calculate for that event happening.
And then you can ask yourself the question, do I understand it? I don't even know what that means, understanding. I have problems with that. Physics describes things, describes phenomena. And as long as it is predictable, as long as that formalism applied in a certain situation gives you the right answer, who cares? Who cares what the meaning is of understanding? I think I leave that up to philosophers. And I think they don't have a clue either, of course, but they... Yeah.
There's a universe up there that we can't see with our eyes, even if we have something 1,000 times larger than this. We have to turn to a different kind of telescope, one without lenses or mirrors or any of the other things astronomers have relied upon for centuries. This invisible universe has to be seen with telescopes that use radio waves, X-rays, infrared rays, or gamma rays. Everything in the universe gives off radiation of some kind. For example, the glaze on this teacup emits gamma waves. Imagine that it is a galaxy, and this Geiger multitube, a crude ray telescope. In the second half of the 20th century, astronomers start exploring the heavens with instruments that are sensitive to a number of different forms of radiation. And when they do, it's like lifting a veil from the face of the universe. There is still no absolute proof that black holes exist. But from the 1970s on, most scientists have come to accept them as real. Incredibly strange, but real.
Because with a neutron star, at least you can imagine it has a surface. And you can land on that surface. And okay, it is a mind-boggling magnetic field, all right, but so be it, it's there. And okay, it rotates 700 times per second. But a black hole has no surface. So you can't even talk about a surface that rotates around. It doesn't exist. And there is no time that you can define. That is pretty bizarre. That goes beyond, totally beyond my imagination. I'll be very honest with you. But yet, it's one of my specialties. I measure them, I find them. Can I envision them? No.
For most of human existence, the question of how everything began is one that only religion dared to answer. But with Edwin Hubble's discovery that the universe is expanding, some scientists begin to believe that they too might have something to offer. Their reasoning goes something like this. If the universe is expanding, then in the past it must have been smaller. Go far enough back and everything must have been crunched together at a point of infinite density. Our universe began, they suggest, when that point exploded, creating the expansion we still see today. This vision comes to be called the Big Bang theory of creation. At the start of the 1960s, scientists are equally divided between this Big Bang theory and a competing notion that the universe is eternal, called the steady state theory. But there's no real hard evidence for either one. In fact, almost no one expects the debate will ever be resolved.
So far, there are no quarks.
Physicists were faced with a paradox. Where were the quarks? Everywhere we looked, we could not find any physical evidence for the quarks. And in fact, some physicists even began to doubt the correctness of the theory. However, over the years, indirect evidence began to trickle in, confirming this theory.
And now when experimenters take a hard look at the proton, they see strong evidence of the quarks inside, and also of the gluon.
Quarks may be real, but they're still pretty strange. For starters, they're so small, it's hard to apply to them our normal notions of size. Physicists describe them as points.
Points? Come on. What do you mean points? How can something have a mass and a charge and be a point? Well, it takes a few muscles in the mind that haven't been worked on. But if you work on them for a while, you can imagine such an object. It's a little bit like Alice in Wonderland. Remember the Cheshire cat sitting on the tree, smiling, and Alice is noticing that the cat is disappearing in front of her eyes, and poof, when the cat disappears, the smile is left behind. You remember that? Well, in a way, you can look at that as you take a quark, and it's spinning, and it's a spherical, if you like, and it has mass and charge and spin and all these other properties that we like to measure about it. But in front of your eyes, it's shrinking. And finally, it poof, shrinks to a point, leaving behind its spin, its charge, its mass, and if it has a smile, leaving behind its smile. That's the idea of point particles.
String theory, quite simply, is the most exciting idea to hit physics since the days of Einstein and Bohr. It may well be the final theory, the one that explains absolutely everything.
The Pythagoreans believed that music was the language of nature, that their harmonies on a violin string, which they worked out for the first time in history, were the harmonies of the universe. And they thought that all around us, surrounding us, was music, the music of the spheres. Unfortunately, that idea never got anywhere, because that couldn't explain the elements. Now we think that if I have a super powerful microscope and could peer into an electron, I would see a vibrating violin string. And when that note changes, it changes into a quark. It changes into gravity. It changes into light. So in other words, our bodies are nothing but collections of strings. And the laws governing these strings are the harmonies of the strings, and they are the laws of physics.
Theorists usually imagine strings as incredibly small, closed loops, more like rubber bands than anything else. Ordinary matter, even space, time, and energy, are nothing more than the vibrations of strings. To physicists, they are beautiful, elegant, simple, everything they dream about.
Then when I integrate
But the mathematics needed to describe them is anything but.
Y, A, B, C, D. My claim is that this thing that I'm writing on this side of the equation is a supersymmetric definition of an index, and the statement is that the topology of the superspace can only be generated by the topology of the bosonic manifold. Mathematics for a theoretical physicist really is an extrasensory organ. I cannot make myself as small as an atom. I cannot make myself the size of a proton. But with mathematics, I have an accurate representation of that, and then I can use my mind to actually look at those small things. For me, the funny thing...
One of the strangest things about string theory is that it only works if there are 10 or more dimensions.
Some people say to us, but that's not commonsensical. That violates common sense. Well, why should common sense have anything to do with the universe? Why should the universe care about your common sense? So we physicists are prisoners We are prisoners of experiment, prisoners of our mathematics, and we simply go where the mathematics, go where the experiments take us.
With string theory, they're going way out. They're using mathematics in a way that physicists have never used mathematics before.
In 10 dimensions, we can look at the entire Clifford algebra of the Dirac matrices. So we have the identity.
They're becoming more and more mathematical, more and more esoteric, unfortunately, and most unfortunately of all, further and further removed from experimental verification. But in a sense, it's the only game in town. It's the only hope we have of unifying everything.
What we are talking about now is understanding all four fundamental forces. That's the power of this theory. We're talking about a theory of the universe. Will it give me better color television? The answer is no. It's not going to give you a bigger toaster. It's not going to give you better sliced bread. But it will give you is a theory that will affect the future course of human civilization. Your great-great-great-grandchildren will one day live to harness the power of the unified field theory.
No one knows if string theory is the final theory. But if it isn't, physicists are sure to keep searching.
Theorists believe 99% of the mass of the universe is invisible to telescopes. If that's the case, it's like a modern Copernican revolution, right? Copernicus told us that the Earth wasn't the center of the universe, okay? Then we learned indeed that the sun wasn't the center of the universe, and our galaxy isn't the center of the universe. Now we're learning that this dark matter, which may be made of stuff which is completely different than anything we see on Earth, is the dominant stuff of creation. That means if you took away you and me and the stars and everything we see in the universe, the real universe would still be there.